In section 8.2, we're going to be talking about interest. We have three main objectives. We want to use the simple interest formula to solve problems. We want to use the compound interest formula to find future value. And we want to solve the compound interest formula for different unknowns, such as the present value, length, and interest rate of a loan. And we'll talk about all these quantities as we go forward. There's a famous quote by Albert Einstein, the famous physicist who gave us the equation E equals mc squared. He said the most powerful force in the universe is compound interest. Let's find out why. Let's start by learning about simple interest. Interest is the dollar amount that we get paid for lending money or that we pay for borrowing money. The amount of money that we deposit or borrow is called the principal. The amount of interest depends on the principal. It also depends on the interest rate, which is given as a percent and varies from bank to bank, and it depends on the length of time for which the money is deposited. Simple interest, what we're going to study first, involves interest calculated only on the principal. To calculate simple interest, we're going to use the simple formula that interest is principal times rate times time, and that's abbreviated as I equals P times R times T. Let's work through example 1. Suppose you deposit $500 in a savings account at Hometown Bank, which has an annual interest rate of 6%. Find the interest you have earned at the end of the first year. Okay, so let's recognize that they've asked us to find the interest. So we're going to use our simple interest formula, I equals P times R times T, and let's just identify what each of these components are. So P stands for the principal. Here we've deposited 500. So our principal is 500. R is the interest rate, and our interest rate is 6%. But we need to convert that to a decimal, so we divide by 100 and we get 0.06. And T is the time in years, and we are told that it is 1 year. Okay. So now we can plug this into our formula. Let's draw a line here to separate our work. So our interest rate is going to be 500 times 0.06 times 1 year. And that works out to $30. And notice that's a reasonable amount. It's important to check that our answers are reasonable as we go through this section. So if we start with $500 that we've deposited and we're getting 6% per year, notice that 10% would be $50. So at 6%, we expect it to be less than $50. And so $30 is a reasonable answer. Here's a problem for you to try. One of the things we're going to be doing throughout this section is solving our formulas for different parts of the formula. So let's use the simple interest formula I equals P times R times T and just some simple elementary algebra to solve for R using the values given below. So pause the video, work this on your own, and then you can unpause and check your solution. Plugging the given quantities into our formula for simple interest, we see that 300 is 1,000 times R times 6. And we're solving for R, so I'm going to divide both sides of my equation by 6,000 to isolate R, and I get R is 0.05, and that is the same, by moving that decimal over twice, as 5%. There's an important note to make here. The problems that we work throughout this chapter don't always have realistic interest rates. In the problem earlier, we had a $500 deposit at an interest rate of 6%, but current interest rates in savings accounts are less than 1%. So finding a 6% interest rate for a savings account is pretty much impossible. So if we were to recalculate that problem using realistic interest rates, let's see what we would get. So pause here, rework that example if you invested $500 at 0.01% for 1 year. Okay, so now we have that interest is the principal, 500, times the interest rate as a decimal. Now 0.01% divided by 100 is now 0.0001. And then of course we still have 1 year for our time. And we see that our interest in this case is not the $30 it was before, it's 5 cents. Just keep that in mind. Savings accounts are not the best way to earn money. Now that we understand simple interest and how to compute interest on an amount borrowed or an amount that we loan someone else, let's figure out how to compute the future value of a loan. The future value of a loan is the principal plus the interest. So the amount owed on the loan after a certain number of years is going to be how much you borrowed plus how much interest accrued in the meantime. So for a loan, the future value is how much you eventually have to pay back. That's principal plus the interest. Okay, so if our future value is principal plus interest, notice that we can rewrite that in terms of the formula we already have for interest. So interest is principal times rate times time, and so we'll see this formula with the p factored out of both terms. So this is p times 1 plus r times t. So the future value of the loan is a equals p times 1 plus r times t, and that p, which is the principal, is also known as the present value. It's the value of the loan right now, and a is the value of the loan in the future once the interest is accrued. Let's work example 2a. Suppose you deposit $1,000 in an account paying 3% annual interest. How much will be in the account after 6 years? So notice they're asking us for a future value. How much will we have in the future? In this case, in 6 years. So we know we need to use our future value formula. And again, let's list out what each of these components are. A is what we're looking for. If we want, we can identify that with a question mark. P is the principal amount, or the amount that we have deposited. So that's $1,000. The interest rate is 3%. We'll write that as a decimal, 0.03. And in this case, the time is 6 years. Okay, now that we have that information, let's just plug that into our formula. Okay, so we plug in the values into our formula. We get 1,000 times 1 plus 0.03 times 6. And we start working inside the brackets first. So we know we need to multiply 0.03 times 6, and that's 0.18. Then we add 1 to get 1.18. And then we multiply by 1,000. And that gives us a final answer of $1,180. And then we notice that's a reasonable amount. Starting with $1,000, if we're earning interest on that amount at 3%, then after 6 years we definitely should have more than the 1,000, and 1,180 is a reasonable answer. Let's work through example 2b together now. If you want to save $2,500 for a whitewater rafting trip in 2 years, and your bank offers a certificate of deposit called a CD that pays 4% annual simple interest, how much must you put in the CD now to have the money for the trip in 2 years? All right, so let's notice that they're asking us for the amount we need now. So how much do we need now? So we're asked to find present value. How much do we need now in the present? And we're told that in the future we want $2,500. So there's our future value. So we're going to use the formula A equals P times 1 plus RT, but in this case we're not solving for A. In this case we're trying to solve for P. So again, let's list what we know off to the side. So the amount that we want, the future value, is $2,500. The principal that we need to invest now is unknown. Our interest rate is 4%, so that's 0.04. And when do we want this money? In 2 years, so T is 2. So we've plugged in all these values, and now we just need to continue solving for P. So what I'm going to do is combine the terms inside the brackets here. 2,500 is P times 1.08. And then we just divide both sides by 1.08. So I'll write this as P is 2500 over 1.08, and you can include the comma or not as long as you keep track of all that. It doesn't matter. And when we work that out with our calculator, we get a final answer, rounded to the nearest cent, of $2,314.81. So that's our final answer, and we would probably just round that up to the nearest dollar for our deposit. Let's continue solving for different unknowns using our new formula for future value. So here's a problem for you to try. Suppose you borrow $2,500 from a friend and promise to pay back $2,655 in 6 months. Under those conditions, what simple interest will you be paying? So pause the video here, try this problem, and then unpause it to see the solution. Okay, so using our future value formula, we plug in 2,655 for A, 2,500 for P, and then 1 plus R is our unknown, and since T is 6 months and it needs to be in years, we record that as 0.5 years. And there are several ways to proceed with the algebra from here. One way is to divide both sides by 2,500. That gives us 1.062 equals 1 plus 0.5r. I can subtract 1 from both sides and get 0.062 equals 0.5r. And then dividing both sides by 0.5, or equivalently, multiplying both sides by 2, it's the same thing. We see that r is 0.124, and changing that to a percent, we see that we are paying 12.4% for that loan. Let's move on now to talking about compound interest. Most of the interest that we are going to encounter in our lives involves compound interest. So compound interest is interest computed on the original principal as well as on any accumulated interest. So with simple interest, the interest is only computed on the original principal amount. But with compound interest, once interest accrues, it's added back to the principal, and then you're paying interest on top of that interest. It's compounded. So with compound interest, after a specified period of time, the accrued interest is added to the principal, and the interest is computed on that new total. And as you might expect, that can really add up. Let's take a look at how we would compute compound interest just using the simple interest formula we already know. And then in a minute, we'll see how we can combine that into a formula so that we don't have to do it this way every time. So suppose you deposit $2,000 in a bank account that pays a very generous 10% annual interest, compounded annually. How much would you have after 3 years? Okay, so that compounded annually means that at the end of each year, they're adding the interest back into your account, and then interest will accrue on top of that. Okay, so after 1 year, just according to our future value formula with simple interest, we start with $2,000 and we end up with $2,200. And that makes sense. 10% of 2,000 is 200, so that's $200 interest, which is added to our principal for a final amount of $2,200 at the end of a year. So when the second year starts, interest is accruing on the $2,200. So at the end of the second year, we add 10% of that, we get $2,420. And we do that again for the third year, and after the third year, we have $2,662. Now, that's a fine way to compute it if we're just doing that for 3 years. But if we were doing it for 30 years, we wouldn't want to do this computation 30 times. So to calculate the compound interest paid once a year, we use the formula A equals P times 1 plus R to the power of T. So now time is not being multiplied by R, it's in the exponent. So A is still the account's future value, the principal is still P, that's the present value, R is the rate, and T is the time in years. It's just that now that time is an exponent because we're repeating that process T times. Now before we go on and work some examples, let's briefly remember PEMDAS. This is our order of operations. So it says if we have an expression to simplify, first we simplify within the parentheses, then we apply exponents, Then we do multiplication and division, and then finally we do addition and subtraction. So let's do a brief review of PEMDAS for our compound interest formula. So if we're trying to simplify, for example, A equals 500 times 1 plus 0.04 squared, so to the power of 2. First, we're going to simplify inside the parentheses. So we get 1.04 inside parentheses. Then we apply our exponent, so we square 1.04 to get 1.0816. And then we multiply that by 500 to get off our final answer. Let's check that this new formula works and gives us the same answer that we got when we computed compound interest the long way. So this is the same problem we did previously. The amount we deposit is $2,000. That's P. Our interest rate is 10%, so that is 0.1 as a decimal. And then the time is 3 years. So let's plug that in. I get 2,000 times 1 plus 0.1 to the power of 3. So I'm going to simplify inside parentheses first and get 1.1. And then I'm going to cube that number. That gives me 1.331 inside parentheses. And an important note, do not round until the end. So throughout this chapter, leave several decimal places past what you're going to need and then round at the very end. Okay, so when we multiply that by 2,000, we get 2,662 as our final answer, just like we did in the previous example, but with a lot less work. Now we're going to define a compound interest formula when the interest is paid more than once per year. So the previous formula was only once a year. So our formula for more than once a year is that A equals P times 1 plus R over M to the power of N. Okay, so this M here, this is the number of times the interest is compounded per year. So the number of times it's added to the principal so that interest can accrue on top of it. And N, the exponent, is the number of periods the money remains in the account. Let's watch example 4 from the e-text.
In this example, we will gain a better understanding of how no payments until ... works. You have seen a home fitness center on sale for $3,500, and what really makes the deal attractive is that there is no money down and no payments due for 6 months. Realize that although you do not have to make any payments, the dealer is not loaning you the money for 6 months for nothing. You have borrowed $3,500, and in 6 months your payments will be based upon that fact. Assuming that your dealer is charging an annual interest rate of 12%, compounded monthly, what interest will accumulate on your purchase over the next 6 months? To determine the interest that has accumulated, we will find the future value of your loan, assuming you make no payments, and subtract $3,500 from that. We will use the formula for calculating future value with P equals 3,500, R equals 0.12, M equals 12, and N equals 6. Therefore, A is equal to P times the quantity 1 plus R over M, all to the power N. Substituting the known values, we have 3,500 times the quantity 1 plus 0.12 over 12, all to the 6th power. Simplifying inside the parentheses, we have 3,500 times 1.01 to the 6th power, or 3,715.33. So the accumulated interest is $3,715.33 minus $3,500 equals $215.33.
Here's an example for you to try. Pause the video here and work this out, and then unpause the video to see a solution. Okay, so first check that you identified all the unknowns correctly. A is what we're looking for. P is 15,000. The interest rate is 0.06. The number of times the interest is compounded is per year is 12 because it's monthly. And then N, notice that N is M times the number of years. And that's 12 times 7, which is 84. We plug all that into our formula, working inside the parentheses first. We see we get $22,805 $1,000,000.54. And notice that's a reasonable increase over $15,000 for a period of 7 years. Let's work through example 5 together. Suppose a parent wants a newborn child to have $60,000 for college when the child turns 18. How much should the parent deposit now into an account with annual interest rate of 4.8% that is compounded quarterly? Okay, so let's try to work on this problem. Notice right away that the interest is compounded quarterly, so we're going to need to use our compound interest formula. And then we need to identify each of our unknowns. So A, the future value, is what we're trying to end up with. We want $60,000 in the future. So that's our future value. What we need to deposit now is unknown. So that's what we're trying to solve for. The interest rate is 4.8%, so that's 0.048. And then M is the number of times per year the interest is compounded. We see that it's compounded quarterly, so that is 4 times per year. And then N is the total number of time periods that the interest is compounded. So that is going to be M times the number of years. So that's 4 times, and then this is going to be 18 years when that child turns 18. And that's 72. And so now we're ready to plug that into our formula. Okay, so we plug that in, and now we need to solve for P. So let's first simplify this expression and see what it equals. Okay, so we find that that quantity is 2.36046,138, so carrying out several more decimal places than we need. And then we just need to solve for P by dividing both sides by that quantity. And we see that P needs to be $25,418.76. So if we deposit that now at 4.8% compounded quarterly, we'll have $60,000 in 18 years. If we want to solve for N in the compound interest formula, so we're trying to solve for the exponent, then we need to be able to solve an equation of the form a to the x equals b, where a and b are fixed numbers and the variable is in the exponent. Okay, so whenever what we're trying to solve for is in the exponent, for example, if we're trying to solve for n in our compound interest formula, then we're going to use a logarithm. So many calculators have a key labeled either log or log x, which stands for the common logarithmic function. You will need a calculator like this for this course. Any scientific or graphing calculator is going to have these functions. And when we use this log function, what it does is it reverses exponentiation. It reverses raising 10 to a power. So if we have 10 to the 5th is 100,000, then if we put in log of 100,000, it gives us back 5. Okay, so it returns the exponent that the base of 10 was raised to. And in particular, it's a way to solve for an exponent. And we're going to need to do that when we're trying to solve for n in our compound interest formula. So there's an important property of logs that's going to allow us to solve equations where the variable is in the exponent. And that property is called the exponent property of the log function. So if our variable is in an exponent, like it is here on the left-hand side, then what the exponent property says is that we can bring it out front and treat it like a coefficient. Okay, so it is the same as just multiplying the log function by that x. So let's work through an example of that. Suppose we want to solve 3 to the x equals 20. Well, we notice that our variable is in the exponent. What we're trying to solve for is in the exponent. And so we have to take the log of both sides. We get the log of 3 to the x equals the log of 20. Right, so I did it to both sides of the equation. And now by our exponent property of logs, that x comes out of the exponent. So now I have x times the log of 3, and that equals the log of 20. And so now I can solve for x by dividing both sides by the log of 3. Okay, so x is the log of 20 divided by the log of 3, And now we just need to use the calculator to find each of those values. So there's the calculator values, and then when we divide those, we get 2.72, and I'll just round that to 7. So you see we were able to solve for x by applying that exponent property of the log function. Let's take a look at the textbook example of using the exponent property of the log function.
Now let's look at an example that calculates the time for an investment to double. Dee Dee has invested $8,500 in old Star Wars memorabilia, which is currently increasing in value at 6.5% per year. If this increase continues at the same rate, in how many years will Dee Dee's investment double? We are looking for a future value of 2 times $8,500 or $17,000. So we can use the future value formula A is equal to P times the quantity 1 plus R over M all to the power N with the following values. A equals 17,000, which is double the original amount of 8,500. P equals the original amount of 8,500. R equals 0.065, which is the annual interest rate written as a decimal. And M equals 1, because the compounding is done once per year. Substituting the values into the formula, we have 17,000 is equal to 8,500 times the quantity 1 plus 0.065 over 1 to the power n. Dividing both sides by 8,500 gives us 2 is equal to 1.065 to the power n. Now we need to take the log of both sides to be able to isolate n. We have log 2 is equal to log 1.065 to the power n. Using the exponent property of log gives us log 2 is equal to n times log 1.065. Dividing both sides by log 1.065, we have n is equal to log 2 over log 1.065, or approximately 11. Thus, Dee Dee's investment will double in about 11 years.
There's a nice rule that we can use to estimate the doubling time of a quantity. All we have to do is divide 72 by the growth rate. So in the previous example, we saw that the annual growth rate was 6.5%. So the doubling time is roughly 72 divided by 6.5, which is a little more than 11. And when we computed the doubling time exactly in the previous example, we saw that it was 11. So this is a pretty good estimate. If you need to compute a doubling time and a rough estimate is okay, this is a great way to do it. Just take 72 and divide by your interest rate. Let's do one final example in this section where we are taking our compound interest formula and solving for one of the unknowns. So in this example, we are told that LeBron is negotiating a new contract. In order to reduce his taxes, he has agreed to defer a $15 million bonus to be paid as $18 million 4 years from now. If his team invests the $15 million now, what is the minimum annual interest rate they need to guarantee that the $18 million is available in 4 years, if we know that the annual interest rate is compounded monthly? Okay, that was quite a long setup, but let's just take a moment and notice that we have compounded interest, so we're going to be using our compound interest formula. And then we also know that they're asking us for the annual interest rate. What is the minimum annual interest rate? So pause here. Spend a moment and try to set up this problem on your own before you unpause and watch the solution. The values for all of the components of our interest formula are listed on the left. So the future value, the amount we need, is 18. And these are in millions. The principal, the amount we have right now, is 15 million. The interest rate is unknown. The interest is compounded monthly, so that's M equals 12. And then the number of periods that will be paid is M times T, so that's 12, and then this is going to be a period of 4 years, so that's a total of 48. So we plug everything into our formula, and I want you to notice here, we do not need to use that property of logarithms, because we are solving for R, and R is not in the exponent. The exponent is 48. It's not an unknown. Okay, so let's walk through the steps of solving for r. So notice that now r is inside parentheses that are raised to a power, so I need to undo what's been done in sort of the opposite order of operations. So before I can get r out of the parentheses, and before I can apply the exponent, I first need to divide by 15. So dividing both sides by 15 gives me 1.2 on the left-hand side. And now I have 1 plus r over 12 raised to the power of 48. And I undo raising something to the power of 48 by raising it to the power of 1 over 48. That doesn't look like an 8. And I have to do that to both sides. So both sides are raised to the power of 1 over 48. And now just a side note here. If you remember your rules of exponents, we know that if we have some base raised to a power, and then we raise that to a power, that is the same as multiplying the exponents. We'll look at what happens if we multiply 48 by 1 over 48. Now that simplifies, so the left-hand side stays the same for now, and we get 1 plus r over 12 to the power of 1. And of course, raising something to the power of 1 just leaves it alone, so I'll just go ahead and erase that. Now we can finish solving for r, so I can subtract 1 from both sides. So I'm going to need to simplify that expression in a minute. That gives me r over 12, and then I can multiply both sides by 12. And we see that r is 12 times 1.2 to the power of 1 over 48. And if you like, instead of having two parentheses, sometimes it's nicer to have a bracket and then parentheses. But you can also just use two sets of parentheses. And then we need to simplify this. So we inside parentheses, when we take 1.2 to the power of 1 over 48 and then subtract 1, that's 0.0038056. And then when we multiply that by 12, we get 0.04566696. And then let's just move the decimal over 2 places, and we have an interest rate of about 4.57%. So the team needs to invest that $15 million in an account with an interest rate of about 4.57 or 4.6% compounded monthly in order to have $18 million at the end of 4 years. And in closing, here's a summary of the interest formulas that we encountered in this section. So we had our simple interest only formula. We had the future value of the account using simple interest. And then we had a compound interest formula. And even though we initially presented a compound interest formula for an annual interest rate, notice that if you let m equals 1, then that's the same formula. So we really only need one formula for compound interest.